All right. Hello, everyone. Welcome back again to GROOT. Today we'll be hearing from Siyong Liu on the generalized McKay correspondence via symplectic geometry.
Yeah, thanks for the introduction. So this is one of the very few papers in symplectic geometry that goes outside of the slightly outside of area of symplectic geometry, and I think that's the something fun to learn about. And well, I will start with an introduction to this so-called McKay correspondence. This is kind of like uh a correspondence between the representation theory and algebraic geometry. So we start with a finite subgroup of the general linear group SLNC, where n is some positive integer, and we consider its linear action on the vector space Cn. And then we want to look at the quotient of Cn by the finite group G. We want to look at the geometry of this. Of course, it is singular because if you look at a linear action, if it is a finite group, it's mostly free outside the origin. But at the origin, it has a finite stabilizer, so that you see that if your quotient by G, the origin is singular. Like in dimension 2, you see it's clearly an orbifold. It's like an orbifold singularity. If n is true, it is well known that the geometry of C2 divided quotient by G, which we also call the Kleinian singularity, if you know this name, corresponds to the representation theory of G, which is a theorem which was proved very early in the 1980s. Now, the first thing is saying that you have a classification of finite subgroups of, sorry, it should be SL2C. The finite subgroups of SL2C can be classified by something called the extended thinking diagram by looking at its reducible representations. So, but extended thinking diagram are just thinking diagrams with an augmentation, so that you will see the thinking diagram are of this form. For instance, this is like an AN, and you introduce a further node at the top, and then you connect the bottom, and you connect the first vertex and the last vertex. So the vertices are irreducible representations. So each one are irreducible representations of the finite group. And this one is distinguished. It is the trivial representation which always appears in every group. Trivial means dimension 1, and the action is identity. So it's just trivial. And the edges are the so-called incidence matrix, where if you look at the linear action on C2 of this finite group, and you tensor with any such irreducible representation, you will get a direct sum of Aij copies of the J representation. So this multiplication is like this is like Aij copies of Rj. So when you take a tensor product, you will get some decomposition, and this decomposition gives you the number of edges from the ith vertex to the j vertex. The vertex is labeled by Ri, and to the vertex labeled by Rj. And this is the representation theory side, and on the geometry side, you can take a minimal resolution of C2 quotient by G, which is not true in higher dimensions, but in 2 dimensions, there always exists a unique minimal resolution. So if you note it by Y, what you do is the only singular locus of C2 mod G is the origin. So you just blow up the origin and then but you cannot, but if you just do this once, you still get some singularities. Because if you blow up this once, you get you get a P1 inside the cotangent bundle of P1, and then but there is still a group action on P1 which has some further fixed points which you need to further blow up. So in the end, what you get is like you get a bunch of P1s. Each of them are -2 curves. And you can look at its intersection graph. And the theorem of and the McKay correspondence tells you that the intersection graph is like you consider each exceptional divisor, each smooth component of the exceptional divisor as vertices. And then if they are connected by some intersection number, you just use the intersection number to label the you just have an edge between them, and each intersection gives you one edge. So this gives you an intersection graph. Or if you want a more topological description, you can say that these are like the bumping graph. Bumping diagram of the standard cotangent bundle of the spheres. If you're familiar with this kind of language, but 3 is actually equivalent to 2 if you just take a closer look at the underlying topology of this space. Bumping means if you start with 2 cotangent bundle of like a sphere, for instance, and you take a disk inside the 0 section. Sorry, you take a conormal bundle of the disk inside. You take a conormal, so say bumping is something like if this is a 0 section of the cotangent bundle, and then you pick a disk inside, and you look at the conormal bundle of the disk. And on the other side, you can do the same. You pick another disk, and you look at a conormal bundle of them, and then you glue these two together. But on one of the conormal bundle, you intertwine between the coordinate of the 0 section and the coordinate of the cotangent direction. So it's like a PQ here, and then it should correspond here to QP. So you swap between these two coordinates, and then you glue them together. Then you get a bumping between these two. And the effect of this is like it looks like a cotangent bundle of S2 with a 1-point union of another S2. So if you have a graph, you can say each vertex is a cotangent bundle of a sphere. And then if they are connected by an edge, you take a bumping of these two. And given the ADE type of thinking diagrams, you just follow this procedure to get a bumping, to get a clumping. Sorry. I made a mistake. Clumping diagram. You get a clumping diagram of then you get a clumping of all these cotangent bundle of spheres, and that is equivalent to the interpretation using the minimal resolution. The only difference is like the symplectic structure is different, but if you ignore symplectic structure, they are diffeomorphic. And that's the all the classifications of the so-called extended linking diagrams, where what you really do is you introduce an action node which corresponds to the trivial representation on each type. And you can also write down like what this diagram corresponds to. For instance, AN corresponds to cyclic group. And DN is just dihedral. And these three are slightly different, but there is a corresponding description where you can just where the classification is actually done by hand, because you are looking at subgroups of SL2C, which is not hard because you can, since this is a finite group, you can actually embed this into SU of 2. This, which is a special unitary group. And this has a description as a quaternion group. The group of quaternion numbers. The automorphism group of the field of quaternion of the ring of quaternion numbers. And using this description, you can just write down the possible generators of G and all the possible relations, which are labeled by, like, each should be generated by three elements, and then there should be some integers that label the relation. It's possibly xa equals yb equals dc. And now the remaining thing is to look at what the possible pairs of ABC can be. And this gives you the following, like, ADE classification. But the story we are looking at is dimension greater than 2. So one thing to note is that since you are resolving C2 quotient by G, the cohomology of C2 is trivial. But when you take a minimal resolution, the cohomology of the minimal resolution is the same as the cohomology of the essential divisors that appearing in the resolution. This is just pi inverse of 0, which is a union of spheres in dimension 2. And the reason is that there is and the reason is actually not so unclear. If you look at the space C2 divided quotient by G, there is an action on well. So if you look at this space, what you're doing is well, this is just a schematic picture. This is the origin, which is singular origin. And you take a blow up here, but it will not affect the geometry of the complement. But the complement, but there is a dilation that contracts everything to the origin, where we call this a sister action. But the sister action is like you have a rotation around the origin, and you have a dilation on the radial direction, which will contract everything to the origin, so that the total topology of the resolution Y is equivalent to the topology of the central fiber, which is the essential divisors. So the cohomology of this is pretty clear because we know the cohomology of P1s. So as a corollary, the rank of the cohomology of Y and Z is actually equal to the number of conjugacy classes of G minus 1. And recall that if you are not good at representative theory, there is a fact that irreducible representations of finite groups are always classified by the conjugacy classes of G. Recall that number of number of irreducible representations of G is actually equal to the number of conjugacy classes of G. But y minus 1, because there is a trivial representation which lies in degree, which corresponds to the fact that H0 of y is actually the same as Z, which is trivial. So even for in higher dimensions, the minimal resolution picture or the intersection graph breaks, you have a candidate. You have a candidate substitution of this result, which is if you just look at the cohomology, there is a similar conjecture. In higher dimensions, we don't have minimal resolutions, but we have Krapen resolution. So what is the Krapen resolution? Krapen resolution is a resolution such that you don't introduce extra exceptional divisors that does not contribute to your so there are no exceptional divisors, or I should say like no extra exceptional divisors that what should I say? So first KY is the canonical bundle. If you are not familiar with algebra geometric language, canonical bundle just means the tangent bundle of Y, cotangent of tangent. The cotangent, the tangent bundle of Y. So what this means is that if you take a resolution, you pull back your singular the canonical bundle of your singular variety to some canonical bundle of the smooth variety, but with some corrections. The corrections come from some possible extra exceptional divisors, and the Krapen condition tells you this thing should not appear. Because, for instance, if you just say like X is just something completely smooth, you can always blow up at the point. But then it will significantly change your topology by introducing a copy of Pn minus 1. So this is the total space of O minus 1 of P, like total space of O minus 1, which is over Pn minus 1. So the definition just wants to exclude this kind of cases where there are some unnecessary blow-ups happening or unnecessary like resolutions happening so that your canonical bundle changes. But this is not guaranteed. So Krapen resolutions do not always exist. And even if they exist, they are not necessarily unique. Not unique means that if you have two Krapen resolutions of a single variety, there are no guarantee that these two Krapen resolutions are isomorphic as algebraic varieties. And the hardest problem is that in this case, the cohomology of Y has various degrees. Unlike in dimension 2, it has only degree 0 and degree 2. Now you have all the possible even degrees. So, but on the other hand, you are still looking at finite subgroups of the special linear group, so that what is true is that the representations are still classified by the conjugacy classes of G, and you only get a single number. So there is a conjecture saying that in higher dimensions, what should happen is that the conjugacy classes of G corresponds to the Euler characteristic of a Clapeyron resolution of the variety. Like that. So it's for instance, it's true in dimension 2 because in dimension 2 it only has H0 and H2, there are no H1, and H0 has rank 1, H2 has rank conjugacy class of G minus 1, so that when you sum them up, you get a number of conjugacy classes. And in higher dimensions, you need to sum up all the possible different degrees. And there is also an implicit claim, which is that all degree cohomology of Y should vanish. Then the Euler characteristic is simply just recorded Euler characteristic is the alternating sum of -1 of the degree of the element times the rank of the deep cohomology. So if all you want to require all the odd degree cohomology to vanish, so that the Euler characteristic is simply a sum of all the degrees of the ranks of all the degrees of Y. So this requires us, if you want to refine this McKay correspondence, you need to say what happens on each degree. And there is a grading on the conjugacy classes of G, which we call the H grading. And the H grading are the gradings that we look at the eigenvalues of the action. Like and any element gives you an eigenvalue, gives you a bunch of eigenvalues from λ1 to λn. And for each eigenvalue, they are in U1 because we implicitly embed G into some special unitary group, which is always possible. And each eigenvalue is a root of unity. Each eigenvalue has norm 1, so that you can write it as e to the square root of -1 times some real number ai, where we just pick a principal value of ai, and we define the H grading of G to be the average of the sum of all these numbers. And because G embeds into SU of n, the determinant of any element is always 1, so that the sum of this λi should be an integer multiple of 2 pi. So you see that the H grading of G is actually an integer. And the conjecture of rate is that if you assume the quotient singularity has a Clapeyron resolution, then the number of conjugacy classes is equal to the rank of the 2K cohomology of Y. Where this is, I need to explain. The number of conjugacy classes of G with subscript K is the set of conjugacy classes such that the H is exactly K. And all the odd cohomology of Y should vanish. And this is the main conjecture. And this is actually a theorem now, but this is the picture of the higher dimensional McKay correspondence. And this is the theorem. And this is a theorem we want to introduce, which is result not by me, but by McLean and Ritter, saying that the conjecture holds. The conjecture is true if the quadrant solution exists. And the proof is purely like a symplectic geometric proof. So there are some notes. So one is the conjecture is actually known by algebraic geometers, where Ito and Reid prove this in dimension 3, where in dimension 3 there actually always exists a quadrant solution. And another group, which is Barty-Rev and Dice, prove the case when G is abelian, which means like cyclic group or products of cyclic groups. And Barty-Rev and another group, Denny-Flusser, prove this in full generality. And there is another note saying that the quadrant resolution does not always exist. For instance, if you consider a resolution of Y to C4 quotient by just the cyclic group C2, consisting of 1 and -1, if it was quadrant, the cohomology consists of the H gradings of all of them, where there are 2 elements, so that you can just directly compute all of them. The first one is identity, which corresponds to grading 0. And the other is -1, where -1 has all the eigenvalues -1, and there are four of them. So you are summing up. So -1 is actually e to the square root of -1 times pi. So you see that the pi is, so this is like a 4 pi divided by 2 pi, which is 2. And therefore, the cohomology of Y has only 2 parts. One is in degree 0, which is a simple copy of Z, and the other is in degree 4. If the quadrant resolution exists and you use the theorem, this will tell you that the cohomology has to look like this, but that's not true. Because the cohomology of Y should be the cohomology of the essential divisor, but the essential divisor is dimension 3. And because you are doing this kind of blow-up procedure, what you get is E is a union of projectives. Projective means compact, and each component is a smooth compact manifold. So that if you look at the cohomology, there should be at least a non-trivial H6. So that's a contradiction. But H6 cannot be 0. Which means that you don't have a quadrant resolution. Every resolution of this C4 quotient by the cyclic group requires requires you to introduce some extra essential divisors in order to make this into a resolution. So that finishes the general introduction part. And any questions? Okay, let's go into the a very brief introduction of how the proof works. But before that, we need to introduce what a symplectic manifold is, which happens for every symplectic geometry talks. So symplectic manifold is actually a smooth manifold with an extra structure, which is the closed and non-degenerate two form, where non-degenerate means So it is a two form. So at each point the symplectic structure is a skew symmetric bilinear form. And we require this as a bilinear form to be non-arbitrary, which means there are no kernels. The kernel of omega should be 0. And there are two examples that we will mainly use in this talk. The first one is a cotangent bundle, where M is a closed smooth manifold, and then you have a cotangent bundle of M with a canonical symplectic structure given by the differential of PDQ. Here I use the vector notation, but this really means the sum of all the coordinates Pi dQi, which is borrowed from physics, where Pi is the cotangent direction, which gives you the momentum, and Qi is the direction of the zero section, or the M direction, which gives you the position. So this is a canonically a symplectic manifold, as you can just check directly. And another case is where M is a Kähler manifold, which is or if you want it to be better, is a projective manifold. Then the Kähler form, which is a 1-1 form inside the manifold, gives you a symplectic structure. And the symplectic manifold M omega is just the Kähler manifold, but you forget the complex structure. So in particular, if you take a resolution of any such quotient singularity, if Y is smooth, then it has a canonical symplectic structure because it's Kähler. And there is one more thing to introduce, where maybe the Y is not a good notation, but maybe I want to use a slightly different notation, which is S. Right. So we say it is a contact manifold is an odd dimensional analog of symplectic manifold, where now you look at alpha is a 1 form. This is not the, well, I should not use omega 1 because it will confuse you with the base loop space notation. So let's use a different notation. Let's say the global sections of the manifold with values in the cotangent bundle of S, which perfectly gives you a smooth 1 form, differential 1 form. And you require that the 1 form together with its differential gives you a volume form on the total space. Well, I should say it's a volume form. And given a symplectic manifold with boundary, there is a compatibility condition for the symplectic structure of M and the existence of some contact structures on the boundary. So the boundary is contact, and the contact form actually comes from the symplectic form by taking a primitive of omega near a Kähler neighborhood of the boundary. So even for omega might not be exact in the total space, omega is exact in the neighborhood of the boundary. so that you can choose a primitive, and this choice of primitive gives you a context structure on the boundary. And this is the mostly technical part of the talk, where I need to introduce some Floer-theoretic things in order to tell you what the proof is. So, but there is a non-Floer-theoretic way of understand this, where if you start with a convex symplectic manifold M, actually what we have in mind is a completion of this, which is a non-compact symplectic manifold, which is M, and then you union the boundary of M cross from 0 to infinity, where along the boundary, where this one is equipped with a symplectic structure, where you use the context structure of the boundary, and then you take where t is the second coordinate, where you take an exponential of this, and then you take the differential. This will give you a well-defined symplectic structure on the we call it a cylindrical end because it actually looks like a cylinder. So pictorially, it is like this is your M, and then you exponentially extend your space. This is kind of a canonical extension because if you try to look at the content manifold and you cross by R, this is the one of the natural symplectic structure you can put on the product. So this is the cylindrical end. And this is and this description of the symplectic cohomology is an oversimplified version where I try not to introduce any of the analysis. So first, it is a cohomology of a chain complex, and for a chain complex, we need to describe the generators and differentials. So generators consist of the two things. One is the Morse cohomology, which is the Morse chain complex, where you just look at critical points of some Morse function on M. There are no symplectic topologies here. This is just smooth topology. And the second part is where the symplectic cohomology comes in, which is the closed orbits of the boundary with the contact form, where the closed orbits of alpha. What do we mean by that? This means, well, so alpha has a canonical dual, although there are no non-degenerate two forms, which is called the R, which is called the Riemann vector field. And well, you can write out the definition as like you need it to be you need a vector field to go as unit length along the context structure, and R is dual. Well, I should say d alpha of R dot is 0. Note that d alpha to the nth iterates, which alpha is a volume form. So in the kernel of alpha, d alpha should be non-degenerate. So this means R is actually kind of orthogonal to the kernel of alpha, and then it goes on the unit direction. So this is the actual dual. So the closed orbits of this, so the Riemann orbits are just orbits of the Riemann vector field, and we also need to count all its iterates. And there are actually gradings that we need to talk about, but let's Just ignore that. By now, it will be very complicated if you try to talk about these gradings. But the differentials are not too bad. The differentials are counting gradient trajectories between the critical points, which are just Morse trajectories. This is how we define the Morse cohomology. And there are some analogs which are going from critical points to rib orbits, which are something like a disk. So this is a critical point, and this is a rib orbit. So you can imagine that you go first along some gradient trajectory, and then you follow some orbits, just some circles, and they finally converge to a rib orbit. And the final thing is just rib orbits, which are just only cylinders, where at the two ends they are rib orbits. And the whole Floer theory is designed to how to make sense of these counts. That's where the analysis come into play, because because after some analysis we find that this actually satisfies some Cauchy-Riemann equation, and then the moduli problem becomes the moduli problem on like finding the space of solutions to the Cauchy-Riemann equation, which requires some inputs from partial differential equations. But we don't need to worry about that. This is the oversimplified definition of the symplectic cochain complex. And the cohomology is the symplectic cohomology. And one thing to note is that we can regard the symplectic cohomology as some sort of generalizations of the homology of the free-loop space. So there is a canonical isomorphism between the symplectic cohomology of the cotangent bundle equipped with the canonical symplectic form with the homology of the free-loop space of N. Of course, you can regard this as some sort of the Legendre transform, where rib orbits of the cotangent bundle are in one-to-one correspondence between are in one-to-one correspondence with closed geodesics of N. Well, including all these iterates. So you will see that the homology of the free-loop space looks pretty like the symplectic homology if you use this definition, because the homology of the free-loop space consists of just critical points of the just critical points of N, and plus the closed geodesics on N, where closed geodesics correspond to rib orbits, and critical points of N correspond just to critical points of the cotangent bundle, which is homotopy equivalent to N. And there is another variant, which is so there is a canonical continuation map from the cohomology of M to the symplectic cohomology of M. Well, of course, as the Morse cohomology is just one of the inputs of the symplectic cohomology, so there is a canonical map between them, and you take the positive symplectic cohomology to be just the quotient, which is just the homotopy mapping cone, which is a homotopy cofiber of the continuation map. And as a cochain complex, you can just see that you quotient out all the critical points from the topology of M, and what remains are just only rib orbits of the boundary of M. And that's the key input of the proof of the theorem. So before we go into the proof, any questions? Actually, I think I'm slightly running out of time.
A quick question then. So it seems like the symplectic cohomology isn't too interesting for manifolds without boundary. Is that right?
Isn't too interesting for manifold without boundary.
Yeah.
So for closed manifolds, there are no such symplectic cohomology. There is a variant of this.
Okay.
So well, let's say like let's add a new page. So so there is an interesting difference between closed symplectic geometry and open symplectic geometry. Open means just with boundary or non-compact. This is symplectic cohomology, and the analog in closed, and the closed analog is the so-called quantum cohomology. And what this is? Well, as cohomology theories, it is isomorphic to the as cohomology groups. The quantum cohomology is actually isomorphic to the singular cohomology. As cohomology groups, I mean like the differentials and the chain. I mean as a chain complex, they are isomorphic. As a homology of the chain complex is isomorphic, but the product structures are deformed. So there are no symplectic topology happening here, but the product structures are deformed. So there are symplectic topology happening here.
Yeah. Okay, that makes sense. Thanks.
Yeah. So okay, let's quickly proceed to like the sketch of how the proof works. So one thing is actually this is true for all spaces with C-star with a C-star dilation, so that everything contracts to the central fiber. That the symplectic cohomology of all such things is always 0. But 0 does not mean it's not interesting, because if you see like if you want to say some such thing which includes the Morse cohomology is 0, then there should be some extra information on the boundary, which is the cohomology of Y should be isomorphic to the positive symplectic cohomology of Y with degree shifted by 1. Based on the long exact sequence we have seen before. So then all the problem reduces to analyze the positive symplectic cohomology, which consists of rib orbits. And how to analyze the rib orbits? Well, you have an isolated singular point here, and then you take a sphere around this. You take a sphere around this singular point, where it should be S2 minus 1 quotient by G. The reason is like well, if you remove the critical point, the G action on the CN removed the origin is free, so that you have a quotient, and the quotient based on the existing of the dilation is homotopy equivalent to the quotient of a sphere by the finite group, which is this thing. And here you can see the conjugacy classes, because if you look at the space of maps up to homotopy from S1 to S2n minus 1 quotient by G, it is actually the same as the fundamental group of S2n minus 1 quotient by G, but the odd-dimensional sphere except S1 are simply connected. So there are no pi 1s, and if you quotient by G, this will be isomorphic to G. Sorry. This will isomorphic to the conjugacy classes of G. And this tells us that if you look at the space of the if you look at the elements of loops inside this boundary, it will be naturally labeled by the conjugacy classes of G. And there is a more direct way to say this, which is if you pick an eigenvector of G with eigenvalue e to the IL, where L is a positive number, then you can get a canonical orbit, canonical loop, which is you just start with this V, and then you rotate around using this, eigenvalue. And we design and we somehow deform or design the symplectic structure of the total space such that the complement is actually isomorphic to the contact structure on the quotient cross the R, so that we make this to be the contact boundary. And we make this to be a Rip orbit by a carefully chosen contact structure. Note that the contact structure is chosen because you can choose a different primitive of the same symplectic structure, and there are some space for you to choose such a structure, and there exists a choice such that you make this into a Rip orbit. And then all the generators of the positive symplectic cochain complex are contained inside this set of orbits such that it is in the conjugacy class of G and with a given eigenvalue, where now we allow this eigenvalue to be from 0 to infinity because we allow iterates. And the theorem is that if you want to compute the symplectic cochain positive symplectic cohomology of the space, the rank will be exactly equal to the conjugacy of the H grid conjugacy of G with the H grading K. And the moral reason for this is the so-called Morse spectral sequence. This is the general way we do symplectic geometry, where if you want to compute symplectic cohomology, instead of using the Morse model, you might want the Morse spot model, where you look at this is the set of all. This is the possible set of all possible Rip orbits. I mean, this Morse spot spectral sequence is that you're given an orbit, which is a Rip orbit. If you want to regard this as a Morse theory, it is degenerate because you have a free S1 action on this, and if you along this around the orbit direction, the differential is always 0. But this is not bad because instead of Morse theory, we can do Morse spot, which means you replace it by the cohomology of the circle, and then in general, you have a family of such orbits, so that you just group all of them together into a single so-called critical manifold, and you take the cohomology of them, and with some degree shifting, so that it is placed in the correct degree. This is actually like a two-step way of computing cohomologies. So the logic is that you have this critical point here, and then at the boundary you have many iterates. But you can use a symplectic structure to make these iterates to be disjoint into each other. So these are all iterates. And each iterate gives you, and you regard each iterate as a single critical point. And now what you want to do is to study the differentials between this iterates. So this is kind of like you break into two steps, and this makes it into a spectral sequence where each column gives you the cohomology of a critical manifold, and the rows gives you these differentials. And the theorem is that it should converge to the positive symplectic cohomology. And we need to see that only one such cycle in each conjugacy class survives. But that's another technical point, and I think I don't have time to explain, where the computation requires you to use the SY equivariant version. And the reason for this is that, well, so for one, we can still well, where does this SY equivariance come from? The SY equivariance comes from the fact that it has a natural action on each orbit. Because here we only look at maps, where XG are maps. Maps are parameterized, and there is a natural S1 action on the map, but if you quotient by S1, you get an S1 equivalent version where each orbits are just honest orbits. They are unparameterized. You identify all the possible parameterizations of single orbits, and this gives you a quotient, GL quotient by S1. And this is good because this is the projective space, which means its cohomology are supported in even degrees. And being supported in even degrees tells you that the spectral sequence, so if you form this S1 equivariant version, where you just replace all the orbits by unparameterized ones and run all the things, and run the construction of the symplectic cohomology again, and you get some analogs of everything. Including the spectral sequence. So then now you consider the spectral sequence of the orbit space, but quotient by S1, which are now only supported in even degrees because it's projective. And well, this is a projective space. With a degree shifting. And for degree reason, this is just degenerates at E2, degenerates. So this just honestly degenerates. So that if you look at so that you have a direct computation of all these things, and the only thing you need to do is to compute the index of each orbit, which is kind of standard in symplectic geometry. And finally, we back to the positive symplectic cohomology of Y, where from equivariant to just non-equivariant version, we can directly use the Guyton sequence, or in a fancy word, it's called the Cornet's exact sequence, because this S1 action this S1 action is intrinsic to the cohomology theory. It is like from Hochschild homology. It is like from Hochschild homology to cyclic homology. If you're familiar with this language. And well, if you combine all these things together, you will finally conclude a proof, because before that we know that the symplectic cohomology is just zero, so that the odd degree cohomologies of the odd degree positive symplectic cohomology is isomorphic to the singular cohomology of Y with some degree shifting by 1. So that odd cohomology corresponds to even cohomology of Y, which means like this one is isomorphic to SH star minus 1 plus minus 1 or plus 1, maybe plus 1. Minus 1, right, of Y, and the rank equals the rank, and then and this one is known to be the conjugacy class, which concludes the proof. Okay, I think I just have 0 minutes, so I will stop here, and thanks for listening.
All right, so let's thank the speaker. And are there any questions? All right, so maybe I'll stop the recording.